School teaches us to view the world in categories. Subjects like history, geography, and art are treated as messy, subjective, and dependent on human interpretation, but mathematics occupies a league of its own. We are taught to see it as pristine, clean, and absolutely certain. In almost every other field of human knowledge, we accept that error is part of the process. We know our historical records have gaps, and our scientific theories might be updated tomorrow, but math is supposed to be immune to doubt. We act as if proving a theorem transforms it into an eternal, unquestionable fact. However, this bedrock of absolute certainty may be an illusion. The very act of doing mathematics is bound by physical constraints that make a flawless, unquestionable proof impossible to achieve. We crave ultimate truth. We want an anchor for our worldview that cannot possibly be wrong. But that desire for solid ground creates a massive blind spot, preventing us from seeing how mathematics actually operates in the physical world. Imagine writing a complex mathematical proof. Your internal reasoning is completely flawless, but someone has secretly swapped your pen for one filled with high-tech trick ink. The physical symbols on the page slowly shift, betraying your perfect logic and rendering your final conclusion wrong. We don't need a prankster to experience this. The uncomfortable reality is that all ink is trick ink. The ink in your pen, the graphite in your pencil, the pixels on your screen, they are all made of matter, and matter always obeys the unpredictable laws of physics. Because our only access to the abstract world of numbers is through physical objects, our mathematical knowledge is always held hostage by physical reality, and physical reality is inherently prone to error. To actually do math, you need hardware. You might use pencil and paper, a calculator powered by silicon computer chips, or simply the firing neurons inside your own squishy biological brain. These mediums are physical objects made of matter. They are ruled by an unstable molecular lattice rather than the laws of pure logic. Paper rots. A cosmic ray can flip a computer's microscopic bit from 0 to 1, and human brains routinely misfire. Calculating an answer, even a simple one, requires a mechanical, physical action to take place in the real world. A mathematical proof is a physical process, a type of computation, and like all physical processes, it carries the possibility of error. The mathematician Alan Turing tried to solve this problem by envisioning a model for calculation using a hypothetical machine with an infinitely long paper tape. He was trying to find a form of calculation so simple that it wouldn't depend on the messy laws of physics. But Turing had a critical blind spot. He assumed his biomedical paper tape would perfectly obey the rules of classical physics forever. He ignored the erratic nature of quantum mechanics and the simple fact that real matter degrades. We see this physical limitation in modern mathematics too. The proof of the four-color map theorem required hundreds of hours of computer time. The sequence of steps was so massive that no human being could read, let alone verify, every calculation in a single lifetime. This leads us to the mathematician's misconception. It is the deeply ingrained false belief that mathematical knowledge is immune to physical errors, and that human intuition alone can confer absolute certainty. Absolutely necessary truths might exist out there in the abstract world, but our human knowledge of those truths is different. Our understanding will always be a fallible approximation, bound by the limits of our physical brains and machines. If we can't be 100% certain that 1 + 1 = 2, it might feel like we should give up on math and science entirely. But we do not actually need absolute certainty to achieve incredible results. Certainty is just a feeling, a subjective emotion. What we actually need is knowledge. We rely on highly reliable, but fallible, knowledge every single day. We use it to build suspension bridges and to calculate the exact trajectories needed to land astronauts on the lunar surface. Mathematics serves as a practical, powerful tool to build better explanations of reality, moving away from a desperate quest for unquestionable dogmas. Abandoning the demand for absolute certainty actually frees us from dogmatism. Admitting that we might be wrong is the very thing that opens the door to continuous, infinite improvement. Mathematics is an ongoing, creative adventure of problem solving, far removed from the rigid textbooks of rules we see in school. Humanity's unique strengths lies in our ability to detect and correct the errors that are natural to our universe. Necessary truth is just the subject matter of mathematics. The actual reward we get for doing the math is the brilliant, fallible explanation we get along the way. The gap between perfect abstract math and our imperfect physical reality provides the exact space where human creativity and progress happen. Don't blame yourself for math mistakes, just blame the laws of physics.